Okay, in this video I want to give you just a little more information about homework number 2 so that you will be prepared to implement that problem and get it turned in on time. And this one is the one that asks you to develop some implementations for 3 different algorithms that are for this class called Approximator. It's in the file approximator.java. Now, on Blackboard, there is a file that I've uploaded which contains the file approximator.java. And I want to be absolutely clear on this. Please pay attention to this. You should use the file that I have provided, approximator.java. It's the file that you see in front of you right here. Okay, if you download that from Blackboard, that's the file that you already use, and that is the only file that you will turn in as your homework completion. Okay, do not make a different file. Don't make 3 programs, don't make 6 programs, don't make a file with a different name. Use this file. Those are the instructions that were given, and I want you to follow those instructions. In this file, you will see several things, and I want to walk through them so that you understand exactly what I'm expecting. And following instructions is very important. The first thing is, I went ahead and put a comment block at the top, which indicates the content that I want you to put at the top. And so, of course, where it says your name goes here, that's where you put your name. Don't leave the braces in. Replace that. So, like for me, I would put Pericopus. Give a name first and then last name. Put your 700 number here. Again, 700, 1, 2, 3, 4, 5, 6, whatever your 700 number is. You don't have to change anything else. This says what the homework is and the course that it's in, okay? So you don't have to change anything else. Just those 2. Okay, put your name, your 700 number right there. Okay, now then we look at the one class that is defined here in approximator.java. It is called class Approximator. And if I go all the way to the bottom, line 93, that's the end of it. And that's just a comment that helps me to remember what it is. Then in this class, there are several methods. Those are what you might call functions or procedures in a different language. But in Java, they're called methods. And so method main, of course, you're used to seeing already. And this signature that you see is normal for the main method. And as I indicate here, again, this is very important. Do not change the main method. Or if you do change it, like if you want to run your own tests and try some different things, it's okay. But be sure to change it back before you submit your finished program. And the reason is that in addition to actually looking at your code and what you've done inside your .java file, I will also just go ahead and compile your program and then run it. So it will run the main, and I'm expecting to see the same output from your program that I get from my program. And the only way that I'm going to get the same output is if you leave the main alone so that it does the same things. And second, if you implement the other 3 methods correctly. The methods factorial, Euler's number, and Leibniz pi. Okay, those are the 3 methods that you are to implement. So this really makes it easy. Aside from changing this comment at the top, there are only 3 places where you are going to be doing anything, right? One place is right here in this method called Leibniz pi, okay? And again, do not change the top line of this. You don't need to change that. There's no reason to change it. What you're going to do is where it says your code goes here, that's where you're going to calculate the algorithm according to the formula that's been given. Now, I've given you a paper version, which is nicely formatted and looks like a math textbook, but then I've also given you this version. Here's how the Leibniz pi estimation algorithm works. It calculates pi as the product of 4, and then this sequence. This is a sequence of numbers where in an alternating way, we subtract a value and add a value. And if you look at it by inspection, you can see how it works. It's 1 minus 1 divided by 3 plus 1 divided by 5 minus 1 divided by 7 plus 1 divided by 9. You can guess what the next term is. It's minus 1 divided by 11. And the next would be plus 1 divided by 13. And you could go on like this as long as you like, right? But how long will we go on with that? We'll go on this many iterations. However many iterations are asked for, that's how long we'll go. So if it asks for 1 iteration, see, I tell you this right here, if iterations equals 1, then the estimate is 4 times 1, so we only have 1 term. See, that's what iterations mean. How many of these terms, okay? So it's only this one, so 4 times 1, the first estimate would be 4. If it was 2, then it would be 4 times the sum of 1 minus 1/3, and that would be it. So what's 1 minus 1/3? That's 0.67 about, and so see, here it is right here. 4 times 1 minus 1/3 is about 0.26, whatever, 0.266, I guess. And then if iterations is 3, it would be this minus that, see, 3 terms times 4. Okay, so that's the way it works. And so you're going to replace this with several lines of code to do this. And then you're going to change this to return the results of your algorithm. So you're going to have a variable that's collecting your estimate and running through using loops, either a while loop or a for loop, to calculate an answer. And whatever variable, whatever name that is, that's what you would return right here. You see, not 0.0. Okay. Factorial is the second one listed here, and it's probably the simpler one of them. Okay. What is the factorial of an integer n? It is the quantity 1 times 2 times 3 times 4 times 5, etc., all the way to n. So if n is 3, then it's 1 times 2 times 3 equals 6. If it's 4, it's 1 times 2 times 3 times 4 equals 24. Okay. Now, I'm going to say something which I wrote in the homework, and if you don't understand what I'm saying, then don't worry too much about it, but because you may not have heard this language before. But for those who might have used another programming language, do not use a recursive solution for this. What I mean by that is do not, within the method here called factorial, do not make any calls to the method factorial. That's another way to solve this problem. We'll talk about that a little later in the course, but I don't want you to do it here. What I want you to do here is to use a loop, a for loop or a while loop. Okay? Note, by the way, that the way that factorial is defined mathematically, that the factorial of 0 is 1. Okay, so that's a case that needs to function correctly. So keep that in mind. Even though, obviously 0 multiplied by anything is 0, the factorial of 0 is actually defined as being 1. Okay, so be sure that you get that correct, and you will see here down in the main, you see factorial of 0 is, and then we make a call to factorial and try to get the answer. Now, the third one uses the factorial function, okay? And the reason for that is that Euler's number, the estimate, is computed as the sum of 1 over n factorial for n in the range from 0 to infinity, okay? You see why, by the way, if your factorial for factorial of 0 were to return 0, then you would have 1 divided by 0 here, and division by 0 isn't something you want to do. But anyway, it's the sum of 1 divided by n factorial for n in the range from 0 to infinity. Well, we're not, to calculate it all the way to infinity would take us infinite time. So we don't want to take infinite time. We're going to do a certain number of iterations once again. Okay. So easily you could see that if iterations is 1, your estimate would be 1 over 1 factorial, which would be 1. If your iterations was 2, it would be 1 over 1 factorial plus 1 over 2 factorial, which would be 1 over 1 is 1, plus 1 over 1 times 2, that's 1 over 2, that's a half, okay? So it would be 1.5. If it were 3, it would be 1 over 1, plus 1 over 2, plus 1 over 6, because 3 factorial is 6, okay, etc., etc. And so the estimate for E gets larger and larger. Once again, your code is going to go here. This is the part you're going to change. you will also change the return value to return whatever variable has kind of collected your results in whatever loop structure you use to do that. So this is Euler's number. Now again, it's using the factorial function. Don't go to Google, oh, how do I do factorial, and then use a factorial function or something that's in the library or in the math library. Yeah, there's something there, but I don't want you to use that. I want you to use your own factorial method that you put in here. Okay, and so you will notice then, as we look at the file approximator.java, if I were to, it's in this directory right here, if I go ahead and compile it, okay, and then run it, like so, you see right now that it gives all of these incorrect answers of 0 because that's what it is told to return. Okay, so as you do this, make sure that you change those values, you insert your own algorithm there, and then that you're getting the answers that you expect for each one. You can look up what Euler's number is. It's about, what, I think 2.78 or something like that. And I've also shown you an example of the output, I think. So it's around 2.78. So you should see, as you look here, that with one iteration, you know what the answer is going to be, right? It's going to be 1, and with 2 iterations, it's 1.5. But as the iterations get up to 25 or so, you're going to see it converge to around 2.78. And you'll see that at 50 iterations, it doesn't really change. One side note, I did have one student who told me that they're getting the exact answers that I was getting up through 25 iterations, but when 50 iterations was called, was indicated there, that theirs actually said infinity. I'm looking into that issue, but if yours does, don't worry about it too much. It may have something to do with a difference of Java on one platform or another, and we might be getting close to with our factorial function of overrunning some numbers on some platforms. So I'll look into that a little bit, but don't worry if your 50 iterations isn't showing the same thing, but all the others are, it'll be okay, so don't worry. Notice for the Leibniz pi algorithm, it takes a lot of iterations really to get a good estimate of pi. So you know what pi is, 3.14159.265, etc. And it's really not until you get up into millions of iterations that algorithm does a good job. And there are better algorithms for calculating pi, but in this program, you're going to implement the Leibniz pi implementation, not the other algorithms. So it's okay. 100 million iterations. On my computer, it's running, of course, just on one core because I haven't made it run on multiple cores. And it's running around 2 gigahertz, and it still takes just a fraction of a second to implement to run the whole program, even when there's actually really code in here. So it's not a big deal. It won't take too long. That's all for this video, and it's probably going to be tomorrow, but I'm going to walk you through another program that might help a little bit with understanding how these method calls work, because I think some of you are a little hesitant about that, but also show you how we might implement another algorithm. In this case, I'm going to implement the Fibonacci sequence, okay, and some Fibonacci numbers. And so it's kind of another math type problem, but math problems are like this are not so terribly hard to understand, and they're really easy for us to do in just a few lines. See, this will be a 64-line program, and after I get the video done for that and upload that, I'll also upload the Java code so you can kind of spend a little time with it if you like, but I thought that might be helpful for some of you to look at as well. Okay? Looking forward to seeing you all on Thursday. Bye-bye.